Okay, let's try this. And like I said, I fear we've got are going to have a rough time today, technically. Let me try one other thing. Let me try to lower the mic. Is this a little bit better? Can anybody hear me in the back through the microphone? Or just because I'm being loud? Are you convinced it's because of the microphone? Okay, since you're all convinced, let me make it louder. Is this better? Okay, let's try it like that. Okay, so let's try to focus and get back to where we are. Break is over. We have to get back to graph algorithms. Any questions, first of all, about anything technically or logistically from what we've been doing? Okay, we're now in the middle of graph algorithms. Last class we had been talking about depth first search. We've talked about breadth first search and depth first search. And we got to the point where we were talking about topological sorting as sort of being the sort of most important, what I will say, is algorithmic graph problems on directed acyclic graphs. And this was the problem of finding a left to right ordering of vertices in a graph, okay, such that all the edges go from left to the right. Here we're talking about directed graphs, okay? The claim is that if you have a directed acyclic graph, then every edge, there's an ordering of the vertices, where a directed acyclic graph, meaning directed, no cycles, there's an ordering of the vertices, so the edges all go from left to right, okay? This obviously wouldn't work if the graph had a directed cycle, because if there's a directed cycle, I can follow an edge to the right, to the right, to the right, but I can't get back to where I was without going to the left. Okay? Any questions about what what I mean by a topological sort? Yes?
What if the graph splits off to two separate branches? Does that mean that it wouldn't be a full sort?
Okay, so let's see. Now we're going to take a chance and go to the coloring here and see if this works. Okay? You're saying if the graph has two separate branches. Now, what do you mean by that? Let's see if, okay, good. This thing looks like it's, let's see if this can be made to work here. Okay, so here is, you mean two separate components like this, or do you mean a branch that goes out over there? What do you mean?
What I mean is, like, in this sort, when you use G, A, B, C, F, E, D, you follow the arrows and go basically through each node in order.
Right.
So what happens if there are nodes that are, one branch would be completely unconnected to the other and has no way to...
Okay, so what you're saying here is, in this particular example, there is an interesting property of this, the topological sort, which is that in fact there is a path through the graph that corresponds exactly to that, right? He's saying, look, you said G to A, there is an edge there, and G to B, there is an edge there, and C, and F, and E, and that, okay? So in this particular topological sort, there happens to be a very special property that it is a path in the graph. That is in general not what the case, okay? If we consider a graph, kabunk, where let's say we have let's say that there was remember one use of these graphs we said was like in maintaining course prerequisites, right? If course A was required before course B, you had to take A before B, and that was a directed edge from A to B, right? What if we live in a world where there's a very lax university, where A, B, and C are courses, and there are no prerequisites between them? In this case, let's say there is one prerequisite here. What are the following orders that are consistent with this graph? Okay, does everybody see? You have to take A before B, but C is unspecified. This is the kind of graph that you say is allowed, right? What are possible topological orders of this graph? There's more than one, right? Yeah?
CAB.
You could do CAB, that's acceptable. What else? Yeah?
AB and then C.
You could do AB and then C. Is there any other one? Yeah? Yeah.
A, C, and D.
A, C, and then B. Is there any other ones that are allowed? The constraint we need is that A has to be before B. Here A is before B. Here A is first of all. Here there is one in between. Those are the only three possibilities, right? So just to clarify what we have now, this should clarify it. The path is not that. There can be many, many different topological orderings of a graph, right? In this particular example, there happens to only be one, okay? What graph on n vertices has the most possible topological orderings of it? Yeah?
A complete undirected graph.
A complete undirected graph would actually have the least possible orderings in it, okay? Let's think about that. First of all, it's got to be undirected. It needs to be directed, first of all. Okay? So it's got to be a directed graph, or we're not in the business of dealing with topological sorts in the business. What set of edges would give me the least restriction on the topological sort? Yeah?
The empty set.
The empty graph. Does everybody agree that if we went to a school like this, okay, where there were these were all the courses, and there were no prerequisite between them. Okay, we have a world where there are six courses offered by this university, right? None are a prerequisite to anything else. You have the maximum freedom to design a schedule. Is that right? Any permutation of the vertices you give will be a topological sort. Okay? Does everybody see that? Okay? So we're trying to find a topological ordering of the vertices, of which there might be many of them, right? Or there might be one. This graph has the property that there is only one of them. Okay? Any questions? Actually, the property that he said here about there being a path on the vertices actually is what forces it to only be one, if you stop and think about it. Right? If I had a graph where I had a path, here I have a bunch of vertices, and again, I'm sorry about the pen today, I know we're going to have a rough time. Suppose we had a graph on here, 1, 2, 3, 4, 5 vertices. There was an edge from 1 to 2, an edge from 2 to 3, an edge from 3 to 4, and an edge from 4 to 5. Right? How many topological orderings are there of that graph? There is exactly one of them. It's constrained by this path. Does everybody see this? 5 can't be before 4, which can't be before 3, which can't be before 2, which can't be before 1. And there's no way to rearrange those 5 vertices such that all the edges go from left to right. How many people see what I'm saying? Anybody confused or any other questions about this? As with all the graph things I'm going to talk about this semester, it's important to understand what the thing is that we're trying to build more than the algorithm. Okay? Because when you have a DAG, you've got to be able to think, why do I want to take a topological sort? And usually a topological sort is going to be helpful for you to do things. Okay? Do you understand what it is and why? Any questions about that? We went through some examples last time. One example I don't think I went through last time. Just of, trouble. Again, we're going to have a hard time today. I'm promising this. Clear, bunk. One example of something that I came up, that came up, which I don't think I talked about last time, that is an example of a topological sorting problem that was important, had to do with something on assembling DNA sequences. Okay, you've heard of the Human Genome Project. Okay, it turns out that there is an important problem of taking sequence data and putting it into bigger sequences by looking for overlaps. Okay, and for that, the details of which are very interesting, but I'm not going to tell you about it. But we have the following problem that's true. Basically, the input is going to be certain strings that are substrings of the right answer, the right genome, along with certain constraints that this has to be to the left of that. It turns out that with so many sequencing technologies, the reads you get come in pairs. And as a result, you'll know that this string has to be to the left of that string. And so you can now imagine the input to the problem is, actually, let me go to the blackboard, because I can tell that I should draw this. Okay, and I'm going to be helpless on that. So what am I saying? There is data here of the form. Here is the human genome. The sequencing data turns out to be you get pairs of reads, and you're told that this string here is going to be to the left of that string there. Okay? So you can kind of imagine that there's a book you're trying to read, and the data you're given are pairs of words, and saying that ACTTG is to the left of CGTTTA. Okay? And you're giving a large number of pairs of these things. Okay? And given a string having to be someplace to the left of another string. And you're giving large numbers of these things, n pairs like that. How can you tell if there is a consistent order for those strings? Okay? The problem reduces to building a graph where the vertices are the different types of strings. There is a directed edge from one string to another string if we have a constraint that this has to be to the left of that, right? Then I'm going to have a directed acyclic graph. A plausible ordering of these fragments is going to be a topological sort of that graph. How many people see what I'm saying? I think this is somewhat ill-defined still. But any questions about it? Okay? But the characteristic of these things is I have some constraints that something has to be done before something else. Okay? How do I find an order where everything is satisfied? Any questions? Okay, good. So let's think about this. So any questions about topological sorting and how you, why it's important? Yes? CLR. CLR is the abbreviations of the authors of a competitive algorithms book. Okay? So Corman, Lieserton, and Revest is another book, okay, that's on algorithms. Okay, it's a good book. It's a more advanced book in some sense than we use in here. But so that example is taken from that book. Okay, so if you want a more advanced treatment of algorithms, go and read the CLR book. Okay. Then they got tired of revising their book and they brought a guy named Stein into the picture, and now they're CLRS. Okay, but that's what that's about. Any questions? Okay. So let's just think what the next thing I'd like to talk about is how do we find the topological sort of a graph, okay? We should now agree that what a topological sort is. It's a left to right ordering of the vertices, okay? How can we actually find such an ordering if the graph is a DAG, okay? And there are two different approaches that I am used to talking about, one of which is conceptually easiest to understand, and one of which is slickest because we know about depth first search. Okay, so let me try to describe the two of them, okay, and then see if we just kind of make sense. What is the easiest way to do it, it's not on a slide, has to note that if a graph has if a graph has a topological sort, okay, let's look at the leftmost vertice here. What is the integree of the leftmost vertice in a topological sort? How many edges go into the vertex that is going to be over to the left, leftmost? Yeah? 0. Why is it 0? Okay, can anybody see why it is 0? Okay, Yes.
Just anything connected to it, it would be a cyclical?
Because in a topological sort, all the edges go from left to right, right? The leftmost edge can't have anything to the left of it to go to it, right? So if the graph has a topological sort, the leftmost vertex has an in-degree of 0. Okay? How many people see this? How many people don't see it? This is important to see, because if you don't see it, then this is something I want to say again. Any questions about why that has to be true? Okay? Further, let's think about it. If I have a graph here, so this says, what does this say? Every directed acyclic graph has a topological sort. This is a statement that is true. In any topological sort, the leftmost degree has to have in degree 0. Correct? The leftmost vertex has to have in degree 0. Further, if we take any directed acyclic graph, can we ever go wrong by picking an in degree 0 to be first in leftmost in the topological order? Okay? If a vertex is of in degree 0, we might as well make it first. Does everybody see that? So what is the algorithm now? The simplest algorithm is to go through all the vertices in the graph, see which one has in degree 0, and put that first. Does everybody see that? Okay? Once we put it first, what are the constraints from the outside edges? Okay, there's going to be edges from that vertex that we put first to other vertices, right? If we put this one first, however, then these edges are not going to be constraints for anything else to come after it. Does that make sense? No. Okay, good question. Okay, let's maybe go back to the blackboard, because I can't feeling bad about my drawing ability here. Kabunk. Let's clear it. Bunk. So let's think about a DAG. Okay, here is a DAG. Let's call it this one, before this one, before that one, before that one, before that one, before that one. And let's call these vertices 1, 2, 3, 4, and 5. Does everybody see this? The directions of the arrows basically go towards the right. So you can see right now that this has a topological sort. You can see it's a DAG, right? But what am I going to say? Find a vertex that is of... Yeah, let me get an edge there just for fun. Okay? I'm going to say find me a vertex of in degree 0. Okay? Which vertex here has in degree 0? Okay, actually it turns out it's funny, you didn't notice. There happens to be another vertex here, like this. Okay? Which vertex has in degree 0? Somebody. Yeah? 3 and 6. I claim we can put either 3 or 6 first. Does everybody see that? Which one should we put leftmost? Let's say 3. Okay? Once we put 3 leftmost, we're now going to finish up the topological sort of the rest of the stuff and put that to the right of it. Does that make sense? And let's start by, if that's true, then we know that 2 is going to be to the right of 3. We know that 1 is going to be to the right of 3. We know that 5 is going to be to the right of 3. Those are no longer constraints, right? Maybe I'll just put them in just to show that we had these edges here, right? Now, what are the in degree 0 vertices? 2 and 6. Does everybody see that we could put either 2 or 6 down now, and it's not going to cause a problem, right? Does everybody see that? So which one should I put next? 2, okay. We could put 6. You want me to put 6? I'll put 6. Okay, it doesn't matter because there can be many different topological orders, right? Once I put 6 there, this edge is now going to be satisfied, right? And now you tell me put down a 2. And when I do that, this guy goes away. What degree vertex now is of in degree, of in degree 0? 1. That's my only choice. I might as well put 1 in there. This and this are now here. Which vertices are of in degree 1? 4, and that's my only choice because 5 still has, no, in degree 0 is what I care about, right? So 4 is the best choice. I would do 4, and then I would do 5. Does everybody see that? That take the in degree 0 vertice that has to exist, because in any DEG there is a topological sort order, and the leftmost vertex is going to have to be of in degree 0. After I put that down and delete the outgoing edges, what's left is going to be a DEG. There's going to have to be another in degree 0 vertex. And by keep doing this, I can peel off the graph. Does everybody see that? I can peel off the topological order. How many people understand that algorithm? How many people don't understand it and want to understand it? Okay, no one. Okay? What's the running time of this algorithm? Let's now think about this carefully. As described in a brutally simple way, as I described it, what am I doing? It seems to me, as I've described it, I am making n rounds of pulling off the next degree, in degree 0 vertex, right? Now I have to find the in degree, which vertexes of in degree 0. How much time does it take to do that on this graph? The graph originally had n vertices and m edges, right? How would I find out if which vertex has in degree 0? Okay, yeah?
I think you would have to check the adjacency list.
I could check the adjacency lists, okay? Of course, it's a little bit interesting because when the adjacency lists, the way that I did it, if you stop and think about it, my adjacency lists are showing the out degree, right? So how would I figure out for a graph that is represented as an adjacency list what its in degree is for every vertice's in degree? Does everybody see that in an adjacency list representation, the ith list is going to be all the edges that go from one out to another vertex, right? The in degree is going to be, what are the edges that go into vertex 1? Yeah?
You don't necessarily have to keep an adjacency list of outgoing edges. You could keep an adjacency list of ingoing edges instead.
Well, let's say, what would I do if I had the adjacency list? Let's think about it. How do I find the in degree of a vertex, yeah?
If you make let's say a Boolean array, and you go iterate through all the edges, and if you find that an edge goes to a vertex, then you say, okay, I found this vertex, and after you go through all the edges, if there's any vertices that weren't found in that way, then you know it has an in degree of 0.
Okay, what you're suggesting is that I keep an auxiliary array that is going to be basically the in degree of each vertex, right? Originally, before I don't do anything, all of them are 0, right? Then what you're going to do is you're going to look through every edge in the adjacency list, right? If I have here in the adjacency list for 1, I have a number 4. What does this mean? This is an edge. What edge is this thing representing? What's the edge that it's representing? 1 going to 4, right? So when I do this, which elements in degree do I bop up? 4 has now got one guy pointing into it. Does everybody see that? The next one here, could be 3. Now 3 has one body pointing into it. In the time it takes to walk over the adjacency list, does everybody see that I should be able to compute what was the in degree of every single vertex in the graph? How many people see how we did that? How much time did this take? In a graph with n vertices and m edges, how much time did this take? Okay, I heard n plus m, and I heard n times n. Which is the one that we like? Yes.
The max of n and m, whichever one's greater.
You're saying the max of n and m. Okay, well, I usually say n plus m to mean the max of n and m, right? Because we're dealing with big O things. The important thing here, this is not n times m, because what are we doing? We're going to initialize each of these n cells originally, right? Then we are going to go walk through each of the n lists, visiting every element in these n lists, of which there are a total of m of them. This is going to take n times m time. Okay? Because we're visiting every edge once, we're visiting every vertex a constant number of times. Any questions about that?
Wait,
Yes.
you said n times m.
I meant n plus m. This is a plus. Okay? It is linear in the number of vertices and the edges, not quadratic. Okay? Any questions about that? Does everybody see this? Now that I've got the in degree, what should I now do? Okay, to find an in degree 0 vertex. How do I find a vertex of in degree 0? Okay, yeah.
You could search the degree list.
I go through this array. Which one is 0? Ding, that is 0, right? So, okay, so one thing that I could do now is to go and search through the list of it, the erector of things to find one of in degree 0. Okay? Yes?
Another thing that you can do when you're removing an edge and you update the in degree, you can check if it's 0 and add it to a special list.
Okay, so one possibility, okay, so one thing to do now is, if we noticed before, let's just finish dealing with, there can be multiple in degree 0 things, right? What if I maintain a stack or a queue of in degree 0 vertices? Okay? Originally it would have been, when I finished this before, it would have been 3 and 6. Does everybody see that? What am I going to do? I'm going to pop the top one off, put that one first in my order. Okay, actually, just to be consistent, I might as well put 3, 6. I'm going to pop it off, put it first in my order, then go through the third list and delete each one of these outgoing edges. What does deleting these outgoing edges mean in terms of wanting to keep track of in degree? Yeah?
Decrementing the index.
I will decrement the appropriate index. Does everybody see this? And as he's noticed, when I decrement it, there's going to be a magic moment when it goes from 1 to 0. Right? When it goes to 0, it is now an in degree 0 vertex, right? Which means that that's its chance to get pushed onto my stack. Does everybody see that? Okay? How many will see the basic mechanisms that I'm doing now? Okay? So what is my basic algorithm going to be here? It is going to be 1, find, basically find all in degree 0 vertices. This we said took order n plus m, right? Then basically 2, while stack is not empty. Basically pop the next vertex, right? Walk through the outgoing edges of V, right? Decrementing them if necessary. When I get a bad one, pop it on the stack, right? And then when it's going, come back to this step. How much time will this take? The first step of finding them was n plus m. Then for each vertex, I'm going to go through its out degree, its number of edges going out of it, once. The total amount of time I spend walking through and deleting edges is going to be equal to the number of edges in the graph. So the total time for this walks over all of these vertices is going to be m. Does everybody see this? And we're going to be going through this loop a total of n times. So this too, if we implement it right, can be done in n plus m time. Okay? Any questions about that? Okay? I know my handwriting is bad, okay? I don't expect you to read it, okay? But I do want you to understand the idea, yeah?
Can you explain the running time of part 2 again?
Okay, so what is the running time of part 2? Part 2, remember, is pull a vertex off of this, okay, and delete all the outgoing edges of it, right? That's what that part 2 step is, right? Now, one way to think about it, if you round up, you can say the outgoing edges of this vertex could be as many as to n other things, right? So vertex I can be adjacent to n other things. If you're determined to give me an upper bound on how much time it takes to delete all of vertex I's neighbors, it's clearly going to be order n. So one way to count this would be to say, we're going to go through this loop n times, deleting all the outgoing edges, and each vertex can have at most n outgoing edges. That would yield a time for this of order n squared. Do you believe that analysis? Okay. Now that analysis is correct, but it's actually a little sloppier than it has to be. Okay? Because a way to count the work, we always are safe if we say there are n steps, each of which takes order n. That's an upper bound. But another way to look at it is to note that the number of times we go through this loop is really not n, but the degree of that vertex. Does that make sense? So it's going to be n times, it's going to be the sum of all the degrees of each vertex. And the sum of all the degrees of each vertex is in fact the number of edges. Okay? So instead of counting it by the number of times through the loop times the biggest amount of time, I want to look at this and just count the total number of things I'm doing, which is more accurately counted by the number of edges. Does that make sense? Okay, this is an important point. How many people get that? See why it is order m and not order n squared. Okay, who sees it? Who doesn't see it? Okay, who's given up trying? Okay, any questions about that? So the interesting thing is this pluck off the zero degree vertex algorithm is order n plus m. Okay? And this I understand and I know how to do it. I had to do some clever bookkeeping here to keep track of the degrees. Okay? But conceptually, this is an easy algorithm. Any questions? Yes?
So if at any point there are no 0 in degree vertices left, there's either a cycle or you're done with the sort?
Right. If there is no in degree, what would happen if our graph did not have a cycle in it? Okay? Every vertex has an in degree of 1 and there's no way to break it, right? So if you're going through this process and there are still vertices in your graph, but none of them have in degree 0, then you say you gave me a cyclic graph. This is not a DAG. There is no topological sort. Any questions about that? Okay? Any questions about this topological sorting algorithm? Because this is one that I understand. If you say naturally, how do I understand topological sorting? This is the way that I understand it. Any questions? But just because that's the way I understand it doesn't mean that's the best way to think about it. So let's look at another algorithm for finding topological sort, which is in some sense much easier and much more obviously linear than what I just did. Okay? What is topological sort going to be? Well, suppose we did a depth first search of a graph. Okay? We talked about depth first search last class. We noticed that they were, when we talked about it, we were talking about it for undirected graphs. But there's no reason why you can't do a depth first search of a directed graph. Okay? and a lot of the same properties, things get subtle, but a lot of the same basic properties emerge. Let's say we were doing a depth-first search of a directed graph, okay? A directed acyclic graph, and we start looking from here. All my edges are supposed to go from left to right. If I started searching from here, the finishing time, I will go discover this edge. I'm going to explore everything from this vertex before I get back to this vertex. That's the thing that depth-first search did. Remember, it started when it discovered something. It immediately explored that completely, okay, before getting back to me. Now, what does that mean? That means that if in the course of a search I have an edge from here to here, this vertex has to be to the left of that vertex because there is an edge there, right? And everything that is discovered from this vertex has to be to the right of this vertex, okay? By nature of this. So really what happens is, if I did a depth-first search of a graph, okay, and I process them, label them in the reverse order of when they are marked completely processed, that turns out to be a topological sort of the DAG. Okay? Because remember, I don't mark something as processed until I have discovered everything reachable. If this vertex is marked completely processed before this one, that means that this vertex is to the left of this one. Okay? How many people sort of see it? Okay? How many people don't see it? Any questions? So what's interesting is, another way to compute topological sort is really basically just doing a depth-first search. And if you take my depth-first search program, okay, which we have in the book and which I put on the slide, and you augment what you do by whenever you see an edge, okay, you check to see whether or not you have a back edge. Okay, whenever you process an edge, you know whether you can classify whether that edge is a tree edge or a back edge or something like that. If I have a back edge on my depth-first search, then it's all over, right? That creates a cycle. So if I have a back edge, I have to write down, warning, you're not giving me a DAG, okay? So I can't topologically sort it. Otherwise, what I did is simply, if you look at my depth-first search, at the end of the vertex, when I mark it processed, if I simply push that vertex onto a stack, where that stack is going to be topological sort, that is all I need to do. Because I'm going to want to list the vertices in the reverse order of when they are finished processing. Okay? And that is also a topological sort. Any questions about that? How many people sort of see this? How many people don't see it? Okay? Nobody's saying they don't, but I know you don't. Okay? But what is the point? Think about it a little bit. Again, the argument that, what is the important thing to capture from this? Is you got to think about it in the quiet of your own home. But what should be obvious? It should be obvious that if in the course of a traversal, this vertex finishes before this one, the one that finished first has to be to the right of the one that finished later. So if there's a topological sort, they're going to ordering them by finishing times is going to be perfectly fine. Okay? That you should be able to understand. It is also good to see, look at my depth-first search process and look at where vertex late is called. Basically at the point when we have finished processing that vertex. All we have to do is to store, if we want to get the order in which they finished processing, whenever I finish processing a vertex, just push that vertex on a stack. The order of this stack is going to give me my topological sort. Any questions about it? Is this going to be linear time? It should be obvious this is going to be linear time, because it's just doing a depth first search and a total of n pushes on a stack. Each push takes constant time, right? So it is obvious this is going to take n plus m time, because depth first search takes n plus m time. It's also, if you understand the subtlety of what basically the ordering of edges in a depth first search, in fact, this gives you a correct algorithm. And that's a little bit trickier to see, but I encourage you to figure that out. Any questions about topological sort? Okay? Any questions? Good. Okay. So what else do I want to talk about to finish up my section on depth first search? I think since we're running a little bit late, I won't talk so much about strongly connected components. I will just give you one foreshadowing of the future, okay? Is we are going to talk in here about a few weeks from now. We're going to talk about exhaustive search procedure, combinatorial search, something called backtracking, okay? Which is about exhausting enumerating all possibilities. Like, for example, finding all possible traveling salesman tours in a graph. That's something we're going to do via something called backtracking. The interesting thing is that when we get to backtracking, that is going to be the exact same idea as depth first search. Exactly the same idea as depth first search. Okay? The difference is going to be that we're not going to have the whole graph in advance. But otherwise, it is essentially depth first search on a graph. Okay? So why should you learn about depth first search? Well, because you're going to see it again in a couple weeks. Okay? And if you understand depth first search, backtracking will be obvious. If you don't understand depth first search, you will be confused with backtracking. Any questions about that? Any other questions about depth first search or any of these application programs that we've talked about? Topological sort, things like that. Okay, good. Okay, now I'd like to get to the somewhat delayed problem of the day, because I think we've now talked through this stuff a little bit. Kabunk, 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 kabunk. Okay, great. So the problem of the day had to do with arranging rambunctious children. The claim was you were given a set of M statements of the form. We have a bunch of n kids labeled 1 through n. Okay, certain pairs of kids hate each other. Actually, certain ordered pairs of kids hate each other. I can hate you, you might not hate me. Okay? The teacher wants to arrange them in a straight line. Okay, why? Because they want to march them down the hall. Now, what is the concern of the teacher? They're all facing to the right. Does everybody see that? If this kid hates this kid, what is he going to do? He's going to take a rock and bunk. Okay? That's what they're afraid of. Okay? What is the way for the teacher to order, given these pairs of kids of relations I hate J? Okay? How do we order the kids so as to avoid any conflicts? What is the idea here? Yes? Two coloring. I don't know what two coloring is, but I don't think that that's it.
Well, you can make them into a graph, an undirected graph. Basically, you don't want them next to each other. And so you have a conflict graph, and if you do a depth first search, and you two-color them, then you order them in that two-color.
Okay, so you want to say that there is a two-coloring of this thing, and a conflict graph. Let's say the answer is maybe, but this is something I don't know how to think about. Yes? Topological sort should seem like the natural thing. What are the vertices? There is a vertex for every kid. And what is the directed edges in this? There's an edge. If I hate you, that is a directed edge. And you're claiming if I do a topological sort, okay, then any time that all edges go from left to right, if I hate you, okay, the edges will now be all left to right. What is the right order for the teacher to arrange the kids? Reverse it, right? This way, yes, if you do the topological sort, there's going to be rocks flying everywhere, right? But if you reverse the topological sort, everybody is helpless, okay? Any questions about that? Yes?
Unless there's a cycle in the hatred graph.
If there's a cycle in the hatred graph, you're out of luck, okay? Any questions about that? Okay? Yes?
So basically, you're putting them in the order where everyone who you don't want it first, then reversing it.
Right, so you take the topological, right, if I hate you, in a topological sort, I would be to the left of you. In fact, the teacher would want me to be to the right of you, so they will simply reverse the topological sort. Yes?
So in this section, do we assume that there is a cycle, or do we say that it is not possible?
Well, okay, so what would I do if I were, if my job is, if my job is to arrange them in an order and there's a cycle, then at that point I complain to whoever gave me this job. That much seems like the right way to do it, right? Any questions? Okay. Any questions? Okay. So the second part here says, suppose, let's say, instead of arranging them in a line, you want to arrange them in a battalion. So that instead of a long line, you have as few rows of kids as possible, where the kids can't throw rocks ahead of them or in the same row. How would we find in some sense, a topological sort with the minimum number of rows here? Yeah?
If we keep a count of the maximum depth that we reach from the first node and perform a depth first search, each iteration of the depth first search would give you a different row of.
Okay, what I think what you're saying here is, if I hate you, and you hate somebody else, and you hate somebody else, if there's a chain of hatreds like this, we have no choice but to use at least that many rows. Is that what you're sort of saying?
I meant to say breadth first search, not that.
Okay, but you're talking about, I think, has to do with the length of a chain of hatreds. Is that right? And that if you have a chain of hatreds that long, you need at least that many rows. Does everybody agree with that? Can anybody give me an idea how I might adopt my topological sort algorithm to try to use a small number of rows instead of n rows, which is what we did before? Any ideas how we might modify our topological sort algorithm to try to use few rows? Yeah?
What is the maximum amount of people that one person hates? Is that the amount?
It's not the maximum. Is it the maximum number of people one person hates? No. Because again, it could be you have one really rotten kid who hates everybody, right? What is the problem, the solution there? Just put that guy at the end of the line, right? He might have to be in a world by himself, right? But if you live in a class where there is one bad apple who hates everybody, one sociopathic kid, what would the world be? You put the kid that hates everybody to the right, and everybody else right behind them. Does everybody see that 2 lines would suffice for that? Right? All the noble kids here, and then they're going to be looking at the sociopath. Okay? How would we figure out the minimum number of rows we need here? Is there a logic? Yeah.
So do the depth first search and find the longest chain.
So you could use depth first search, find the longest chain. Yeah, I guess so. And now how do you assign everybody else? Okay? So maybe. Any idea how you would think? What about the first algorithm I gave? Is there a natural way to modify that? Yeah?
When you try, what is that, all of them in the row, instead of the one by one.
Right. What if instead, if I have a lot of in degree 0 vertices, all of these guys have the property that they could all be, lest, right? Why don't I make all the in degree 0 vertices lest as a battalion, right? Then delete all of these. This will create a new bunch of in degrees 1 0 vertices. Then put them in those stages. Does everybody see that? That we're going to treat them in groups of in degree 0 vertices. And this, it turns out, will minimize the number of stages. Any questions? Okay, and the reason why that works is one in degree 0 versus another, it doesn't matter where they sit in topological order. You might as well have them go at the same time. Any questions? Okay, good. Okay. So, that said, I'd like to now change gears and start talking about weighted graph. Yes, question.
I'm sorry. So, could you explain that again for the part B?
Okay, so what is the idea here? The important point here is in our previous situation, we had a topological sort algorithm. We said find an in degree vertex, 0 vertex and put it first. It's clear that if there were multiple in degree 1 vertices, 0 vertices, they could all be first. So we might as well make them a cohort and put all of them first. Then delete all of their outgoing lines, edges. That will create another set of in degree 0 vertices. Put them all simultaneously. And so it's doing them in groups. Okay? Any questions? Yes? What would the running time of that algorithm be? Okay? My instinct is it doesn't change at all from the previous analysis. Right? Except what are we going to do? We're going to first go and count all the in degree 0 vertices. Right? Put them into our stack. Now, we want to omit all the in degree 0 vertices from the stack. Let's copy them down and put them at the end. Then delete all of the outgoing edges from these. This will create new vertices, which we'll now put on the stack. We're doing exactly the same work as before. We're only going to be reporting them basically in waves. Is that convincing? Face doesn't look convinced. Okay? But if you think about it, I don't want to go through it more than this, but I think this should be clear. Okay, think about it. It's basically, what are we doing? Let's just take a look at it again. If you think about it, based on the in degree 0 vertices, originally we had a set of vertices on our 0 stack, right? All of these, before we do any deletion, we'll mark these as being in wave 1, right? Then we're going to go delete them. And after we delete them, okay, every in degree 0 vertex we create now is going to be in wave 2, okay, until we delete our first wave 2 vertex, at which point we're going to label them as wave 3. There's really no additional stuff that we're doing here, other than labeling vertices when they got put into the in degree 0 queue. Okay? Any questions? Yes?
And so each wave is a separate line?
Each wave would be a separate line of students. Exactly right. Where you have all the in degree 0 those students there, then after we take once these guys are here, anybody they want to throw a rock with no longer is a concern, and we put the remaining new in degree 0 vertices right behind them. Any questions? Okay. Now I'd like to get back to weighted graphs. Or not get back to, tell you about weighted graphs. We talked about them when we talked about graphs in general. A lot of graph problems, none of the ones we've talked about so far, but a lot of graph problems relate to things where there is a natural edge weight to them. What problems did we talk about? Depth first search, breadth first search? They're just walking over a graph, the edges of the graph. It doesn't matter how big the edges are. Okay? We talked about topological sort. There's nothing meaningful numerically on the weights of the edges. We talked about finding bridges and articulation vertices. And there's nothing meaningful about the edges, the weights of the edges there. But for a lot of graph problems, the weights of the edges are important. The most obvious one is shortest path. We talked about this. where if you want to find the shortest path between here and California, it's not the number of roads you go on, but it is going to be the length you travel on each road. And so if each road is augmented by how long that road is, the length of your travels is going to be the sum of the distances you travel on, of the edges you travel. Okay? So for a lot of problems, like shortest path problems, make sense on weighted graphs. And so for the rest of the unit on graph algorithms, I'm going to talk about basically two big killer apps of weighted graphs. Okay? Finding minimum spanning trees, and then finding shortest paths. Any questions about that? How do we represent a weighted graph? Really, in a weighted graph, the edge is going to be typically weighted. Usually you could have vertex-weighted graphs or edge-weighted graphs. Usually the interesting things happen when you weight the edges. Okay? We are going to augment our edge structure in an adjacency list by having an extra field. So far, when we had an adjacency list, we had an array of vertices with a linked list of edges coming out of the ith vertex. Up till now, what was our edge structure? What was the other vertex y, okay, that I is adjacent to? And what is the link to the next edge in this adjacency list? In a weighted graph representation, all we are going to do is add an extra field to our edge structure, okay, which is going to store a weight. It could be an integer weight or a floating point weight. But it's going to represent, in the case of a road network, the number of, the distance you travel, on the distance this road link takes, or how long it takes to travel. On a friendship graph, maybe it's going to measure how close a friend this person is. Does that make sense? You probably on your Facebook page, there's probably people who you're really close to, and somebody who you regret ever adding as a friend, right? And so you could imagine having a numerical number, maybe weighting the friendship strength. That would be a way to turn the friendship graph, the Facebook graph, into a weighted graph. Okay? Any questions? But in general, weighted graphs are useful things. Any questions? So the mother of all weighted graph problems is something called minimum spanning tree. And it's a problem which is, I'll explain why I want to talk about it. The shortest path problems, which we'll talk about starting next class, shortest path makes sense to everybody, because everybody has wanted to find the shortest path between one place and another. Minimum spanning tree is a problem you may not personally have ever wanted to do, but still turns out to be a very natural and important thing to do on graphs. So what is a minimum spanning tree? Well, a tree, as we've said, is a connected graph with no cycles. That's what a tree is. We talked about trees many times. A spanning tree of a graph, okay, is a subgraph, meaning a subset of edges, such that it has the exact same set of vertices as the graph. And those edges form a tree. So what does this mean? Let's say we have a graph like this. This graph has some edges. Okay, let's say here is, trouble. That's going to be bad. Here we've got let me try one more time. Trouble. Now we're in big trouble. Go away. Trouble. I knew this was going to be bad today. Okay, let's clear this one out. Is this here? Okay, clear. Okay, let's look at, here we've got a graph where we've got 1, 2, 3, 4, 5 vertices. A spanning tree is any subset of edges that forms a tree on these vertices. So, for example, this here, this this. God damn it. Oh, God. That would be a spanning tree on the graph. Why? Because the set of vertices are the same, and it's connected then. Actually, let me just draw this again. I'm sorry. I'm going to give this up here. So if we give you a graph here, okay, here's a graph, here are some edges, okay, what is a spanning tree of this graph? Okay, any subset of edges, okay, which form a tree connecting all the vertices would be a spanning tree. Does everybody see that on this particular graph, the green edges would be a spanning tree? It is a tree, there is no cycle created, okay? And every edge is a is an edge of the original graph, and we visit every single vertex. This would have also been a spanning tree of the graph. Okay? Does everybody see that? What graph has the fewest spanning trees? Can anybody give me a graph that has the fewest number of spanning trees of it? Yeah?
A tree.
A tree. If the graph I gave you originally was a tree, how many spanning trees are there? Well, you need all those edges. You can't delete any of those edges. Okay? So this graph has exactly one spanning tree. Which graph has the most spanning trees? Okay, which graph has the most spanning trees? Yeah? A complete graph. Does everybody agree that if I have a complete graph, okay, then there are going to be a large number of spanning trees. How many spanning trees will the complete graph have? Okay. Can anybody give me a, yeah? How many?
Is it like n factorial?
Like n factorial, something like that is exactly right, okay? Why is it n factorial? Let's think, why did he come up with n factorial for that? Well, he noticed that a special class of spanning tree would be one where the tree was just basically a path, right? And he noticed that, in fact, in a complete graph, once you specify basically any permutation of the vertices would be a legal complete path in that graph. Is that right? So in fact, there are at least n factorial possible spanning trees of that graph. How many people see that reasoning? Okay? In fact, I think the number is n to the n minus 2. Okay? But if you take a good enough graph theory class, you'll figure out why. But that's not important. The point is there's a lot of them. Any questions? Now, a minimum spanning tree, if I go down here, is going to be of a weighted graph, is going to be the spanning tree, okay, whose sum of edge weights is minimized, okay? Now assume we have an edge-weighted graph, okay? There are a large number of potential spanning trees, okay? One of them, if we add up the weights of the edges, the edge weights will, the weights of those, the tree edges will be minimized, okay? That is the minimum spanning tree. Any questions about that? Is it clear that a graph may have many, many, many different minimum spanning trees? It should be clear if my graph had every edge weight, if I had a complete graph where every edge was of weight 1, any spanning tree would be a minimum spanning tree. Does everybody see that? So when you tell me I want to find the minimum spanning tree, I will say, no, find a minimum spanning tree. It's clear that there can be more than one minimum spanning tree, right? Doesn't have to be more than one, But in certain graphs, there can be a lot of different minimum spanning trees. Does everybody see that? Based on what we know now, can anybody give me a correct algorithm for finding a minimum spanning tree? Okay, and not necessarily efficient, but what would be a correct algorithm for finding a minimum spanning tree? Yeah?
Construct all spanning trees and figure out.
Search through, construct all minimum spanning trees, add up the number of edges we see, and if this is lower than the best one we've seen so far, keep it. This is a correct algorithm, but it is going to be an exponential time algorithm, right? Any questions about that? Okay. Actually, how would we go find a spanning tree of a graph? Let's not worry about a minimum spanning tree. Suppose we want just a spanning tree. How would we go and find a spanning tree of a graph? Yes?
We could start at some random edge, and some random node, and for each edge, choose add it to let's say a heap of edges.
Okay, well, I'm going to stop you here because I like to think about, again, I always tell you designing graph algorithms is very hard. I don't design algorithms, graph algorithms, but I think, is there something I know? Yes. If I do either depth first search or breadth first search, do I build a spanning tree along the way that I do that? And the answer is yes. My discovery relationship is going to be a spanning tree on the graph. Does that make sense? So in fact, if I want to find a spanning tree, I do depth first search or I do breadth first search. The tree of discovery will be a spanning tree. So finding a spanning tree can be done in what time? N plus m, linear time. So finding, if I'm happy with any spanning tree, I am happy, right? If I want to find a minimum weight spanning tree, if I try to do this by searching all possibilities, I am doomed to exponential, right? In fact, there is going to be a cleverer algorithm for it. Okay, and that's like two of them, and that's what we're going to be talking about next time. Oh, this time and next time. Any questions? So let's talk a little bit about minimum spanning tree again. Oh, what am I doing here? How did I move this? Bunk. Uh-oh, trouble. Hold on. How did I move this forward? Let's just try kabunk. So let's just think about, let's look at a very special case. This is an interesting example where suppose we were dealing with the vertices here are points in the plane. Think on the A, okay? And let's think that the distance, it's a complete graph. For every pair of points, okay, we keep track of the distance between it is going to be the Euclidean distance between those 2 points. On the right, you see 2 spanning trees. Which one of these is going to be a minimum spanning tree? Okay, is it going to be B or is it going to be C? Okay, B.
If it's a scale, I guess it's B.
Well, in this particular case, it's definitely going to be B. Okay, B is the one that is going to have the lower sum of edge lengths. If you look at it in graph C, all the edges are very long, right? In graph B, in the spanning tree B, there's one long edge and a bunch of short edges. Does everybody see that? Okay. So why is it that people care about minimum spanning trees? And there are several reasons, okay? Some good, better than others, okay? One is, okay, so why do people teach minimum spanning trees, okay? One reason is there are a bunch of applications that it comes up in. And I'll try to discuss some of them today, although some of them may sound a little hokey to you, okay, just because you haven't experienced them yet. A second reason is that it's going to be an important example where what we call greedy algorithms always give you the optimal thing. I showed you that there are n factorial-ish spanning trees. There are n factorial-ish traveling salesman tours. You can't find the traveling salesman tour optimally by starting from one vertex and always walking to the nearest edge. But somehow that works for minimum spanning tree. And looking for why does the algorithm, sort of the simple, greedy, grab the next best thing algorithm, works for minimum spanning tree, is interesting. Okay, it's a representative that there are certain problems for which making the best local decision is the right thing. And minimum spanning tree is a canonical representative of that. And the other thing that we're going to be dealing with, why we're going to care about it, is that to make the minimum spanning trees efficient, algorithms efficient, you need to use the right data structures. Okay? And I'm going to want to talk about that, just to sort of make sure so we understand how you engineer efficient graph algorithms from a basic idea here. Any questions about that? Okay. So what is there, let's go back to Bunk. Okay, clear. So why is it that people care about minimum spanning trees? Okay? The original reason you care about it has to do with if you're trying to connect, let's say you work for the phone company. Here we've got a bunch of points representing houses, okay? And let's say the distance between pairs of houses is their Euclidean distance. And let's say that the cost of connecting them by a wire, by cable television, is proportional to the length of the wire. This kind of makes sense. If you have to put 3 miles of wire to connect my house to yours, that's going to be more expensive than if I have to make a 100-yard connection. Okay? So if we think about what we would like to do, if the edge costs are going to be the cost of connecting those two houses by a wire, okay, what is natural is that the tree, to connect them so that a signal, they can all share, let's say one of these points is the source signal for the television. If they're connected by wires, all of them can see the signal, okay, if you have a connected spanning tree. And if the cost of building an edge is the weight of that edge, the cheapest such tree that you can build is the minimum spanning tree. How many people get that application? Any questions about that application? Okay? I think most people can look at that and say, sure, but I don't work for the cable television company. Okay, so what does that mean? Let me show you one other, maybe I'll talk it through, hold on. Kabunk. One other application that is common has to do with clustering, data clustering. This is something you probably will do, okay? Sometimes you are given sets of points that look like this. So these are 2 points, maybe they're plotted in some XY space, okay? Each dot may represent a person, where let's say the x-axis represents how smart they are, and the y-axis represents something else, okay? It's a bad example, maybe their weight, okay? And if you gather data like this, sometimes when you look at the data, you see a certain number of clusters standing out. How many clusters of points do you see in this example? 2. Does everybody see 2 points of clusters? 2 clusters of points. How would you teach a computer, given as input a set of n points? How would you teach it to figure out how many clusters there were? Okay, do you see what the clustering problem is? This is a very, very important machine learning problem. The input was the XY pairs corresponding to all the points. XY, 1 dot. So each point you get its coordinates. The output you would like to say is all of these points are in one cluster, and all of those points are in another cluster. How would you program a computer to try to figure that out? This is a natural thing to want to do. Does everybody see what the problem is? Okay, this is a natural thing. How would you find a clustering of these points? Okay, yeah? Say minimum spanning tree. What does minimum spanning tree give you if you take the minimum spanning tree of this thing? I can tell you, what do you think the minimum spanning tree would look like? It probably has a lot of short edges there. It probably has a lot of short edges there. And it probably has ka-chung, one big edge, linking the two of them. Does everybody agree that the minimum spanning tree of these points looks something like that? Right? So how would you find the clusters of these things? Find the minimum spanning tree and do what? Yeah?
Look for edges that are some threshold.
If I have an edge that is too big, delete it. And that will make my cluster, leave me with clusters. Does everybody see that? Okay? So a lot of clustering problems, data clustering problems, reduce to finding minimum spanning trees. Okay? Any questions about that? Okay? So there are a bunch of reasons why people want to find minimum spanning trees. Okay? Let me, before we go today, just describe to you what is going to be the first algorithm to find minimum spanning trees. Okay? And it's an algorithm called Prim's algorithm, which is going to say, start from, we know that in a minimum spanning tree, the tree is going to be connected. We know every vertex will appear. Prim's algorithm is going to start from one vertex and grow the rest of the tree one edge at a time. And what it is going to do is repeatedly pick the cheapest edge it can to grow and add another vertex to the tree without creating a cycle. You can't create a cycle if the graph is going to be a tree, because trees don't have cycles. We want a cheap tree. Let's try adding cheap edges one after another. Okay? Let's look at this. Clear. Ka-chunk. Ka-chunk. Okay? Let's look at the graph and see what the example is. Let's say we have a graph over here on the left, and we start from vertex A. What is the cheapest edge that is adjacent to A? Adjacent to something that is in the tree. What is the weight of that edge? 5. I might as well add that. What is the cheapest edge that is adjacent to my tree? There's 2 that are weighted 7, right? Which one am I going to grab? Well, I don't care. Maybe just to be a little controversial. Look, they get the same answer as on the other tree. I'll get that. What is the cheapest edge I can grab now? Vertex I can grab now. Okay, I can grab one. You say if 3, that's exactly right. I can grab that thing. What is the cheapest thing that I can grab without creating a cycle? 2, I might as well grab this one, right? What is the cheapest thing I can grab without creating a cycle? 2. What is the cheapest thing that I can grab without creating a cycle? Does everybody see what this process is? This is an easy process. It's a logical process. Now, it's basically consisting of what? N steps of each time trying to find the next smallest edge. There's only one thing that should still not be completely clear to you. Does this produce the right minimum spanning tree or not? It should be clear it produces a spanning tree. It should be clear that it feels good to always grab the cheapest edge. But it should not necessarily be clear, in fact, it's obviously unclear, whether it produces the optimal spanning tree. If you tried to do this with traveling salesmen, it would not produce the optimal tour. So next class we're going to look at this and figure out why is it that this gives us the optimal tour. Thanks for your attention. Talk to you guys then.